measure the gravitational field. The gravitational field, as you go on higher, the magnitude of the acceleration due to gravity is decreasing, and at every point it's pointing towards the center of the Earth. So that's a vector field. You're associating a vector with at every point. A vector is pointed along the z-axis. Find the flux of the vector field through a rectangle in the xy plane between x equal to a and b, and y. Do the same through a rectangle in the yz plane. Leave your answer as an integral. That's because the integral is hard to do. Okay. So x is between a and b. X is between a and b. So here's a, b, and y is between c and d. So this is your area. Okay? And your vector field is pointing in that direction. And you see, as you go further away, xy square, that's the locus of a circle centered at the center. As you're going further away, the vector field is getting weaker. Okay, so here's how it looks like. Okay. It's getting weaker, okay? And it has a constant value along those circles. So the trees are of equal height at those points. All right, so there's a vector field. Find the flux of the vector field through the rectangle. Okay. So there's the vector field dA. Okay, dA, here's the area dA. dA is V is alpha x squared plus y squared z hat. dA is dx dy, that's the sides dx dy, and the vector is pointing in the direction of z hat. All right, for this, we are doing the integral over this surface. Do I draw a circle on this integral? No. This is not an enclosed surface. If you were doing the integral over the surface of a basketball, that's when you draw the circle. Okay, so this is an open circle. Okay. So this is equal to alpha x squared plus y squared. Alpha is a constant, dx by dx dy. So this is a two-dimensional integral, this surface integral, okay? And x goes from a to b, and y goes from c to d. Okay, so you could do that integral, but it's a little hard to do, so we'll just leave it at that. Okay, so that's the flux. Okay, so we'll write down that's part A. For part B, we're going to do the same through a rectangle in the YZ plane. So, okay, and the area is in the X hat. Okay, so this area. So this flux would be V dot dA, which is alpha x squared y plus y squared z hat dotted with dy dz x hat. And of course, the vector field is in this direction and this area is in that direction. They're perpendicular to each other. Z dot x hat is 0. So, of course, if you look at this vector field is not penetrating that area at all. Okay. And similarly, if you draw an area in the xz plane, that area is not being penetrated by that vector field.
Can you go back just for a second? To the second part being.
Mm-hmm. Consider the uniform electric field equal to that. So this is the jth component, this is the y component, z component. What is the electric flux through a circular area of radius 2 meters that lies in the xy plane? So the area lies in, okay. So this area vector, okay, can you give me the vector form of this area vector? What is the magnitude? Pi. Mm-hmm. Mm-hmm. Okay. So the flux is the subscript E telling you that it's an electric flux. It's E dot area. And I'll write the 10 to the power 3 in a second. Dotted with pi r square k hat into 10 to the 3. Okay, so k dot k survives, j dot k dies. Okay. So it's 12, no. What happened? Okay, that's 412 pi.
When does the circle with the I, the J, and the K, and the negatives, is that for cross product?
That's for cross product. I cross j equal to k. I cross j equal to k. J cross k equal to I. What is I cross k? Hmm? Negative j. Thank you. The electric flux through a cubical box, 8 centimeters on the side, is this much. what is the total charge? Oh, this is turned out into an English problem. So the electric flux through a cubical box, 8 centimeters on the side is that. So the flux is given, the flux is equal to the charge inside divided by epsilon naught. Okay, so charge inside. So the charge inside is epsilon naught times flux. And the flux is 1.2 into 10. The Newton cancels. Epsilon naught has Newton meter squared. The Newton cancels and the meters cancel, and you're left with C. So into 10 to the minus 9 coulombs, 8.85 into. So the charge is 10 nanocoulombs inside this cube, somewhere inside this cube. Gauss's law won't tell you where it is. Okay. When will the charge be right in the center of the cube? Okay, so the total flux is that. If I told you that the flux through this face is 0.2 times 10 to the 3, can you tell me where the charge is? So the flux through one of the face is 0.2 times 10 to the 3 Newton meter square per coulomb. Then can you tell me where this charge is? So what I did was I divided that by 6. It has 6 faces. I told you the flux through that one face, so the flux through the other faces are the same. So that charge is in the center. Okay? And that's, yep.
Why is that the case if on a sphere
Mhm.
it's not in the center?
Oh, no. All we said was, okay, so the point we were making was the following. So here's the surface. If the charge is here, there's more lines going through here than here. That's all we were saying.
Oh, okay.
And so if what we said was if flux through every face is the same, that means the charge must be in the center. Yeah. All right, let's do this one. A vector field E, not necessarily an electric field, is given by this. So you see, a vector field, you're associating with every point a vector. Calculate E dot n hat dA, where S is the area shown below. Assume n hat is k hat. Okay. So the flux is E dot dA. And the area is, so a small area element is dx dy, okay? So dA is dx dy k hat. So flux is 3x square k hat dot dx dy k hat. And x goes from 0 to a, and y goes from 0 to a. So this is x cubed times y. So the flux is a to the power 4. So again, you're learning to do simple two-dimensional integrals. Okay? Surface integrals. Okay, two parallel conducting plates. Again, this, you'll see this in the next chapter. These are parallel plate capacitors, two parallel conducting plates, each of cross-sectional area 400 centimeters square, are 2 centimeters apart. See again, it's a large area, very close together. Okay? Does that make sense to you now after you've had?
What's the cutoff?
I think we need the paper explanation.
Oh my god.
Oh, well, this certainly is, these are not infinite plates anymore.
Is there like a formula for the cutoff?
No, there's no formula.
It's just like
I think the whole point is that it's so big there couldn't be a formula.
I mean, there's,
Well, this is 0.5%, the ratio.
yeah.
So I'm thinking it's like,
Mm-hmm.
like the distance, like delta x is on the bottom,
Mm-hmm.
like the distance between the papers, and then you take the limit as that goes to 0, and it makes the top go to infinity. Like the size of the paper is on the top, distance between them on the bottom, limit as the bottom goes to 0.
That's not zero.
Yeah,
No,
well,
it's
yeah, I
very-
mean,
it's very
it's,
close to 0, so the
Well,
top
none
is
of
very
it's
close
zero.
to infinity.
It's like the distance between them will never be 0, but the distance, like the
Distance.
size of it is so big that we can call it infinity. It's not actually infinity, it's just the idea of it being so big.
In
I can just
relation
accept
to,
I'll
like,
just accept it.
the
Yeah, okay.
area, the size of the area in relation to the small size of the distance.
Couldn't you just like think of it like an asymptote, like it never fully reaches there, but you could just call it infinity,
mm,
Yeah.
kind of?
it's approaching infinity.
Yeah.
So two parallel conducting plates, each of cross-sectional area 400 centimeters square, are 2 centimeters apart and uncharged. Okay, so here are the plates. They are uncharged. And then what you do, if 10 to the 12 electrons are transferred from one plate to another. And that's what happened here. See in this thing. So what you're doing is, when I connect the battery, what I'm doing is I'll send electrons from here to there, and these electrons will repel these electrons, which will come over here. So this plate will get positively charged. Okay? So electrons float from here to there, and nothing crossed the plates. It's just that these electrons repel these electrons. If you stretch a spring, have you stored energy in it? What kind of energy? Potential energy. When these plates get charged, what are they wanting to do?
Get neutral again?
They are trying to attract each other. So if you are maintaining this, it's like a stretched spring. You've stored energy here. That's what you did. You transferred energy from here to there. And again, why did you transfer it here? Because this device will release its energy very fast. When you have when you want to shoot a laser gun, energy is transferred from here to there. Okay, you can't use a battery and shoot a laser. Okay. All right, so if a trillion electrons are transferred from one plate to another, so then if you take electrons from here to there, this becomes positive and this becomes negative. The charge density on, what are the charge density on each plate? So so this became positive and this became minus Q. The charge density is given by the total charge divided by the area of the plate. And what was the charge? The charge was n, the number of electrons, times the charge of each electron. So that's the magnitude of the charge. So a trillion electrons. What is the charge of an electron? That many coulombs. And area is 400 centimeters squared. Okay, so coulomb per meter square. So let's do this. That's 10 to the minus 15, 10 to the minus 3, 1.6 divided by and this would be, so I'll make this 0.4, another 10 to the minus 3, so 4 times 10 to the minus 6 coulombs per meter square. Okay, 4 microcoulombs per meter square. That's the charge density. What does this number mean? Every meter square, a meter square would be this much. A meter square of that surface would have 4 microcoulombs of charge. So that's what that surface charge density means. Okay? The electric field between the plates. And the electric field between these conducting plates, these are conducting plates.
For part B, when you just divide that by the E naught or whatever the constant is.
So the electric field between conducting plates is sigma. That constant is called the permittivity of free space. Okay, so this will teach you an important point, Coulomb square and Newton meter square. Okay, this is 10 to the power, this will become 10 to the power 6, and 4 divided by all right, so what we found was you charge these plates and the electric field between the plates is this value. Does this value ring a bell? So there's a point to the story. Does this number speak to you?
It's almost as much as light.
Okay, so this is less than 3 times 10 to the 6. You put more charge, this increases, and the electric field increases. You get to 3 times 10 to the, if this field got to that, then this air would become conducting and the plates would discharge. All your money would go out the window. The more charge you put, the more energy you're storing. So there's a limit to the amount of energy you can store in a capacitor.
And that number is 3 times 10 to the 6.
The limit is set by that thing.
Is that when it starts turning the molecules to plasma or whatever?
That's right. So it makes it conducting.
It ionizes the air, right?
It ionizes it. Yeah. So you want to be able to store more and more energy. So what do?
You put more conductors and
Where the-
Increase the area.
You stuff it with plastic.
oh, so you insulate the gap?
You put something called a dielectric. So it does two things. Now you can, so I'll show you a neat picture in a second. Now, what does the dielectric do? It prevents the plates from coming together. So you have mechanical support. And so So to create lightning in air, you need a field of,
3 times 10 to the 6.
Yeah. Here's lightning in Teflon. For lightning in Teflon, that's what the dielectric strength is. What is the electric field strength you need to turn it from insulator to conductor? In Teflon, you need 60 million volts per meter. 20 times greater the electric strength. So you put Teflon in between those plates and, you can store more energy and all that kind of stuff.
Can you store more energy if they're further apart?
Okay, so the capacitance, here's how much energy you can store, CV square. And C, the capacitance of a parallel plate capacitor is epsilon naught A D. If they're closer, D is the area between the plates. If they're closer together, the capacitance is higher, you're storing more energy.
Okay.
And if the area is greater, then you're storing more energy. So supercapacitors have large areas, and we'll talk about how you make the area large. I can make a large capacitor with an area equal to this room, but then how I'm going to walk around with it in my pocket, right? So we'll talk about that. All right, we'll do one more problem and that's it, okay? This one. A long silver rod of radius 3 centimeters has a charge of minus 5 microcoulombs on its surface, microcoulomb per centimeter. So lambda is, remember, when you put a charge on a metal, it resides on the surface. Per centimeter. Of course, we want to convert that to 10 to the minus 2 meters. Okay. It's minus 500 microcoulomb per meter. That is lambda. That's the linear charge density. Find the electric field. Find the electric field at a point 5 centimeters from the center of the rod. Okay. When you're outside the rod, so again, this is a common theme. It's here's Earth, and if you're outside the Earth, the force of gravity on you is, it doesn't matter if you turn the Earth into a black hole, the force of gravity on you would be the same. So if the Earth's International Space Station is going around the Earth, and you flip a switch and make the Earth into a black hole, turn the Earth into a black hole, the orbit of the International Space Station won't change. Yep. So,
Why?
the gravitational force on it is the same.
Because the black hole would have the same mass as the Earth.
It would have to have the same mass as the Earth. Yeah. Okay. All right, so outside, the electric field is the same, so, all right, let's, and the electric field from a long, infinitely long wire is given by that. Nine times 10 to the, okay. Lambda is minus 5. Five centimeters. The negative sign just telling you that the field is pointing inward. Yeah? Let's take Gauss powers of 10, that's 10 to the 9, 10 to the 11, 10 to the 13, the 5 dies, oh, there's a minus, so 10 to the 7. Two into 9, 18 into 10 to the, so the electric field is 180 into 10 to the 6 Newton per coulomb. So the electric field 5 centimeters from the rod is that. What is that telling you? Lightning. You can't put that much charge on this rod. It would spark. Okay? Yeah. And in part B, find the field inside the conductor, the field will be 0. Okay? All right, guys.